Good afternoon, everyone. I'd like to thank AMAP for inviting me here to speak today. For those who don't know anything about Delaware, it's the 49th largest state in the Union. Delaware starts the Mason-Dixon line, and you can think of Delaware as a state that's about 100 miles from north to south and about 20 miles wide. We also only have one area code. I know there's many counties in California that are far larger. DelDOT owns and maintains 90% of the roads and bridges in the state. We do anything from suburban roads to the interstates. Since this is about polymer modified asphalt, it varies from year to year, but approximately 20% of our asphalt used is PG 7622, and we put down about 100,000 tons of polymer modified asphalt. Okay, let's see if everything works. Oh, great. Short history on the MSCR test. It was developed by John D'Angelo at Turner Fairbanks in the early 2000s. It became a provisional standard about 2008. The test was developed for two purposes. One was to better characterize rut resistance, which is your JNR, or non-recovered compliance. And the other was to characterize polymer modified asphalts, which is percent recovery, because the PG system developed out of Sharp, which is M320, Ashton M320, is blind to modification. The elastomeric curve moved around in the various permutations of the standards. It now has ended up in R92. It used to be as graph X1 in M332. So the test is now split between T350, which is how to run it, M332, which is specification, and R92, which is elastomeric curve. The Z factor, just plain Z, really uses the R92 elastomeric curve. The name Z factor was coined in 2014, give or take a year, by Greg Harder. I was at a meeting of the Northeast User Producer Group, and they were talking about the MSCR test. It was still early on. I said, you can explain part of the problems you're having by looking at the distance from the elastomeric curve. Greg called that the Z factor, and he's been a champion of it ever since. Okay. A lot of us find this test confusing. I still get phone calls occasionally from a hot mix plant and say, have you approved this source of number 20 oil? 20 oil, we're talking about MSCR. That's as far removed as Gregorian chance is from Metallica. Anyways, briefly, the MSCR test is based on your climate grade. Delaware is a PG 6422 state, so our climate is 64. Our standard grade would be PG 64S for standard, minus 22. The old 7022 becomes PG 64H minus 22, and our polymer modified 76 is now PG 64E minus 22. Some states are 100% MSCR, especially in the Northeast. Most states are still PG graded, which is M320. Delaware is mixed. We use PG 64E minus 22, which is the MSCR spec for polymer modified, but everything else is a PG system. And but we will accept MSCR grades interchangeably. What I'm talking to you about today is sort of a hands-on approach and a way to get a better understanding of your binders. Sometimes I feel like the two characters in Chaplin's movie. Okay, how it all came about. Early on, I was fascinated by the test and got from our DSR manufacturer the software to run it. So in 2008, I was running with polymer modified asphalts. And so I took a sample and ran it and heated it again a few days later and ran it a few days later. And as you expect with any reheating, it would get stiffer and stiffer. You see it in the DSR. Every time you reheat a sample, it goes up about 1 or 2%. So then I plotted against the elastomeric line, and I realized all 3 points ran parallel. Okay, this should be the laser. Basically, these are running parallel to the elastomeric line. And it dawned on me that even by abusing the sample by reheating it, I was basically keeping the same distance above the line. And so that later became called the Z factor, or just plain Z, and they range from 2.9 to 2.7, 2.5, so they're all pretty much the same. The equation is at the bottom. This is only the equation you really need to see. This is basically the equation in M332, the old M332 graph X1, R92 when they published it in 2018, referenced the equation but did not include it in the standard. All you do is put in the JNR that you measure, and it will give you what the percent recovery is at the elastomeric line. You subtract it from the percent recovery you measure, and you get your Z, which all it is the distance above or below the elastomeric line. So this makes for a very quick talk at this point. But that was 2008. It was early on. And I said, okay, maybe this is just unique to Delaware. 2 years later, the Asphalt Institute with Greg Harder coordinated with the Northeast group a round-robin MSCR test. There were 23 labs involved. Some of the labs, this is the first time they ran the test. And they sent a sample of PG 7622 along with other samples. And the 7622, they treated it two ways. One, they gave you a tin of the original binder. You had to run it through your RTFO oven because the MSCR test requires an RTFO aging. And then you ran the MSCR test. The other sample they gave was they had pre-run a large amount through the RTFO oven and gave each lab a pre-aged sample with specific instructions on how to heat it. And so now you get two different graphs. The red squares happen to be the preheated RTFO that the Asphalt Institute gave to each lab. And you can see, ignoring the few clunkers because it's early on, basically the whole cluster runs parallel to the elastomeric line. When the labs were given the sample, the original binder had to run it through the RTFO and then run the test. It's still parallel, but a bit lumpier, because now you're having two variables, the variability of the RTFO oven, the variability of testing. This really just shows the testing. And so it gave me the idea that I know agencies and suppliers always argue, well, is it this or that comes to grading? So if there's any differences, they'll talk about, well, our JNR is different than yours. But when you look at the distance above the line, that really means you have the same asphalt as far as elasticity. So this distance is the factor, and on the curve it's probably about like 8. Okay, so far, two key points. The Z or Z factor, as Greg Harder calls it, is a distance above or below the elastomeric line on R92. Two labs can have different JNRs and percent recoveries, but the Z between the two will be near constant. So let's look at a few examples. This happens to be a collection of split samples from our suppliers, covering about a 2.5-year period from 2017 to 2019. I'd originally drawn the graph as our data versus their data, but they overlapped. What you're seeing is not, oops, back pedal. Oops, how do you, okay, how do you get back on this? There we go. Too many buttons. This is not our lab versus the supplier's lab. What you're seeing here are basically two different base stocks used for making the polymer modified asphalt, and they'll behave differently. They're above the elastomeric line. but you can see they're quite different. And you've heard all the talks in the workshop today, and yesterday and earlier. It's tricky putting a polymer in an asphalt, and that's why you're seeing basically two different curves. Okay, this is a standard JNR percent recovery, which everybody does. So we're going to pop it over to the Z factor. This is showing you how high it is above the curve, how elastic it is. A lot of them hover around here, which is a Z factor of 10, but you have this other group from the different base stock. Obviously, I had to put in more polymer to get the JNR stiffness. The more polymer you put in, the more stiffer it will be. And so, the more elastic. Okay, this I took, and it's a single supplier using their split samples. This is Del.'s lab data. And since most people look at JNR and percent recovery, I put it on a timeline. It covers 2.5 years. The JNR is the yellow triangles. To put on the same graph, I had to multiply it by 100. And then the blue is your percent recovery. And the red line is at 50% recovery, or 0.5 JNR, which defines your E-grade asphalts. And it's sort of hard to understand what's happening here, because everything's overlapping. And so I put it on, let's see, as a Z factor. Now it becomes a lot clearer what's happening. Okay, you start to see, for one supplier, because unfortunately we went in a 20 or so year period from 4 refineries down to 1. The one refinery does not make a polymer modified asphalt, so everybody is now buying it on the open market and modifying it. So here you have one base stock, because you realize a supplier will not put in any more polymer than they need to meet the grade, because polymer is expensive. But on the other hand, they will not purposely sell you a product that fails. So here's one base stock, here's another, all within the same year. You get a third one here, and then this looks pretty much like that with some of that. Okay, that's all fine and good. And you can see over actually several months how much it shifts. Now let's pretend we're a lab doing mixed design. And most people do their mixed designs in the fall and winter when things are very quiet and calm and not being beat to death with a lot of paving activity. So this is in the fall. So let's say this is a product you're using for your mixed design. And you do all your tests, your rutting, your cracking, and whatever else test you use to prove your mixed design. You say, this is a great binder. We're ready to go for the next paving season. Next paving season comes, you start to get something like this. And you say, why isn't the testing behaving the way it did back last fall? And so, and this problem actually has cropped up. And it cropped up in New Jersey DOT. It was the same sort of issue. Tom Bennett was kind enough to give me the data. He's from Rutgers University and does a lot of mixed design testing for New Jersey DOT. This is their high performance thin overlay, which has a very rigorous performance test criteria. One of them was rutting. And so they did their mix and everything was fine for a few years. And all of a sudden, come the paving season, they were getting rutting. And it was these asphalts here. Notice how close they are to the elastomeric curve. And so he switched suppliers and everything behaved very nicely. And what he got, the second group, was up here. Now, a high performance thin overlay is really only about a 3/4 inch or 1 inch thick pavement of a high polymer content, high asphalt content layer and it's used in New Jersey and New York City. But when you look at the graph and you convert it to Z, these are very consistent. The Z is about 8 percentage points above the line. These here are in the 20s, somewhere around 24 and 28. And what I find most interesting is the J and R here is the same for this group and that group, so they're equally stiff, but this is far more elastic. So just looking at J and R will not explain everything in your polymer modified asphalt. Yes, it's stiff, and yes, it's above the line, but how elastic do you need it? In his application, he needed a very elastic asphalt with basically a Z of somewhere around 24, give or take. We had the same problem and approached it from a different direction. We too, in Delaware, specify high-performance thin overlay. This is taken right out of our specifications. This is what we give to the supplier and the contractor. It's a nominal 76 minus 28, but we've written it 4 different ways as both a M30 320 and an M332, which would be the MSCR test. It was written as a regular 7628, that's fine. We also do a 7622, but we specify the BBR values. And if you crunch the numbers, it's really a 76 minus 27, because we really don't need a 28, and it does give the suppliers a little bit of wiggle room. Now this thing over here, this equation, is basically your Z factor, but Z factor is not an official AASHTO terminology. And so I took the same equation and say, if it comes out to 25 or greater, so this would be a Z of 25, then you have an asphalt suitable for high performance thin overlay. And let's see, hopefully this is backwards. Nope, maybe this is backwards. There. So what Tom Bennett found by trial and error for his high performance thin overlay, he needs something around a Z24, 26, something like that. And DelDOT going a different direction, because we tested various binders, we also came up with the same value. So we both converged at the same point for the same product by 2 different methods. Okay, Greg Hardy gave me this slide for one of his presentations. New York State, unbeknownst to me, actually specifies Z in some of their binders. And they actually track it. They have a Z of above 0 and a Z above 8. And they track how much. So another state's DOT is actually using the concept. So I guess I'll have to go back to our standard spec book and change that formula to just call it Z. Okay. Greg Harder came up with a paper about 2 years ago now, in 2018, and he called it, "Is your PG64E different from are PG64E binders your father's PG76?" They published it in their magazine. He has gone and given several presentations. I borrowed the illustration from his article. And in the old PG system, the M320 system, since it's blind to modification, some states put down as a maximum phase angle on the original DSR at 76 degrees of 75 degrees phase angle to get the elasticity. And this was one of his common plus specs. And when John D'Angelo came up with his curve, he actually went around and sampled asphalts that various DOTs, and suppliers said this was a good polymer modified asphalt, and the curve was basically based on his empirical data and hand-drawn. So here are your higher phase angles, and here's a phase angle at 75 degrees, and these would be phase angles lower, like 70 and 69. And so he put it on the response curve, and it came out to a percent elastic recovery of 40%. I'm going to go back to a slide. 1, 2. Okay. At 0.5, you're at 35. That's what the curve is. So this is 5 points higher at 40. And the original curve that was drawn in the provisional standards had the curve at a JNR of 0.5 at 40%. So the question is the PG different 7622 versus 64E? The answer is yes and no. It doesn't meet the 75-degree phase angle, but they're fairly close. Okay, now let's look at some data. I took the data from one of the other graphs, and here is the elastomeric curve in R92, one we've been using for basically a decade, and here it is at the 75-degree phase angle, which in the old 7622 regime was considered minimum for a polymer modified. And you can see there's a bunch of samples that fall in between. Yes, they meet the R92 curve, but they're not quite up to what the old 76s were in some places. So should we have multiple elastomeric curves? And some people have said, yes, well, I need a stiffer asphalt, so the curve should be drawn up here, and some say, well, you need a curve here. And then you have proliferation of curves. And in the Northeast, you're dealing with 12 states, which is from New England to Maryland, from Maine to Maryland, which is a quarter of our states, an area not much different than the size of California. And it drives suppliers and refineries nuts when you have multiple specifications. Well, I want it to this curve, I want it to that curve. So the answer, my answer, is no. Just use a Z factor. If you need something more elastic, specify. I want a Z of +5. That will push up the curve. Or in Tom Bennett's case, I want it to +25. So please don't make multiple curves. Okay. It's a tool. I talked briefly about polymer modified asphalts, especially the high polymer modified, such as the high performance thin overlays. But you can use it elsewhere. Now, if you look at R92 in the AASHTO spec, it's fairly rigid. It's strictly for polymer modified asphalts. It's strict, it has nothing to do with S grades, which are your standard grades. And at JNR of 0.1 or lower, anything over 55% recovery is considered polymer modified. So it's a very rigid box. The next slides and the rest of this presentation will be trying to understand your asphalt better by working outside the box. And sometimes in the job I feel like poor Charlie Chaplin. Okay, so there it is outside the box. Your standard grade starts at 2.0, so from here over is not an R92, but I extended the curve out. I also tested the standard grades, which is not in any of the MSCR specs for using this curve. Down here are your 6422s, which we use in Delaware. This would be a 6428. As a straight run binder, you have to make it a little bit stiffer to get the extra elasticity because it's a stretch grade. And so as you stiffen the binder, it will have some percent recovery. Now, this line of unmodified asphalts runs pretty much parallel to the elastomeric curve, and the distance ranges somewhere between -20 to -22, which is a very useful tool, because now you know what's happening to binder. Is it acting like a non-modified, or is it acting like a modified, or somewhere in between? Now this was done in 2010, 2012, before anybody accepted it as a state standard. And so this shows, these are PG 7022s, unmodified stretch grade. All these little red squares are 7622. I took our 76s, ran it through the MSCR test. They all meet 7622, without a doubt. But going back to Greg's, is your 64E same as your grandfather 76? Look, they are different. Some are way below the elastomeric line. They were happily called 76s and people bought them and used them. Some are way up here. Now these black circles, which actually run parallel, are RAP. RAP is basically an oxidized asphalt. And so it just follows along as an unmodified binder. When you get up around here, you're starting to see roofing asphalt. There's a roofing plant in northern Delaware 10 years ago, about the time this was, we were doing the test. We got a sample, ran it through the MSCR test this way up here. If you use post-consumer shingles, these are post-consumer shingles. This is what the MSCR is for post-consumer shingles. Yes? We did not use the elastic recovery test because there are probably about 2 or 3 different versions in the Northeast on the temperature you ran it at. We just accepted it as polymer modified.
So it was just straight AASHTO M320.
Straight AASHTO M320.
Okay.
This is what you got from good old M320. They all met 76. Thank you for the question and clarification. So basically RAP and RAS are oxidized asphalts until you get up to about percent recovery between 30 and 40. They run parallel to this curve. From here to here is still about 20 units. Okay, so now we're thinking outside the box. Now I'm going to take this area here and blow it up and talk about it in greater detail. Okay. What you have are your 76s. This is stolen from the other graph. The elastomeric line, this pale blue line is the E grade. Back in 2010, E didn't exist. V for very heavy was considered to be a 76, and with enough testing they had to put another grade, and they called it the E. So all these met 76. Here's our good old 7022, here's your RAP, and your RAS is way up there. If you look at GNR 0.1, which is right here, and R92 says if it's 0.1 and you're over 55% recovery, it's automatically polymer modified. This sample RAP, according to that definition, is. But it's below the curve. And so it's really an oxidized asphalt. Now I got 2 samples down here. This is ground tar rubber. This is where you throw whatever it is, a 20-30 mesh into your hot mix. This has actually been blended out of plant where they blended the binder with the ground tar rubber and then ran it. And it meets the 7622. J and R is actually 0.5, which would actually make it an E grade. But look, it's right along here, this line of unmodified. Now what's happening? If you look, I mean, tars are bouncy, you can bounce tars, and rubber's bouncy, but why isn't this elastic? You look at the ground tar rubber particles in asphalt as raisins in raisin bread. It may make it stiffer, but what you're measuring for your percent recovery is not the raisins, but the bread, the continuous phase. The continuous phase happens to be your base asphalt, which is some unmodified asphalt. And so your percent recovery in your NASCAR basically looks like an unmodified binder. And the same thing happened in the presentation I had earlier today about graphene, and it was from Mihai's lab. They put in lots of graphene, and when they ran it, it fell right down here, right where it was an unmodified binder. If you did a Z of it, it would be minus 20 or minus 22, because the percent recovery was measuring the continuous phase, which is your asphalt binder, and not the graphene. You had a hot mix plant experimenting with a portable mixer. And you've probably heard 1,000 times today that polymers hate to dissolve in anything. And asphalt's a poor solvent. So you put the two together, something that doesn't want to dissolve and something that's a poor solvent, it's hard to make a polymer modified asphalt. And it takes a lot of stirring, mixing, and grinding, sometimes 24, 36 hours. Portable mixer mixes a small batch for a few hours. It gets stiff. We made our 7622, it passed that. But in the short time, you don't fully open up the polymer, which starts off as a ball, and as you work it in the solvent, it opens up and then starts to entangle. And your entanglement will give you your elasticity. So this is somewhere between an unmodified binder and a polymer modified binder. So this is a Z, what I write down, of about minus 12. It's about 12 points below the line. It has some polymer in it. And we had a presentation just before lunch by Cooper from Louisiana, and they were having problems with their 7022 with latex, because you put enough latex to meet this line, it became a snotty, globby mess. And so they said, we'll just make it, it has to meet a H grade at percent recovery of 15, which would be over here, and it would be a Z. He could actually specify it as a Z number of minus whatever he found works. And this is where your lab has to test out your materials and see, especially if it's in between, what works. Just like Tom Vinert tested out, he needed a high Z, and Sam Cooper said, well, I don't need the full elastic, I can deal with minus something, but not minus 20. So far, so good? Okay, PG64S. We're a 6422 state, but probably only about 10% of what we use is 6422 because we use a lot of wrap. And so we use 5828 or 6428, which is actually great for New England, and it took us about 2 years begging for a supplier to actually stock some in the greater Delaware area. And 6428 is a stretch grade. You talk about UTI. This is a big one. And it's hard to make a straight run 6428. To do it really well, you need the heavy Boss can crudes, but Venezuela has tons of problems with their oil wells. Oftentimes you have to fiddle with it to get it to happen. So here is basically a straight run 6428. It might have some modification, might have vacuum tower oils in it, it might have whatever pixie dust they put in. But when you get up here, and these are split samples that we have run, you get up here, for this base stock, they had to put in a small amount of polymer to get the large spread in properties, because you couldn't get it with a straight run binder. And so here, you have a small amount of polymer, and if I was specifying a 6428 with a polymer, I can specify this distance, which is, what did I write down? Z of minus 13. Because if this is 20 to 22, this is about 7 or 8, and this is about 13. So it's Z of minus 13, does not meet the elastomeric curve. And everybody thinks if you put polymer in, it has to meet this curve. No, it doesn't. This is in the S grade, which is not on R92, but you can specify a partially polymer modified binder if you need to, either as an agency or as a supplier. Hopefully you mutually agree. And the agency, if they specify a partially modified binder, they have to do their homework. Does it meet the performance? You put in polymer, it costs money. And something will be more expensive, but because it's competitive, these are the same price. Okay. Going to 6428. The phase angle of the original DSR pretty much corresponds to the percent recovery. If you talk to Tom Booner, and I agree with him, the phase angle of your RTFO aged binder is more accurate, but Delaware, every time we have a hot mix plant running a state project, we pull a sample from their tanks, they're oftentimes in line, and run the original DSR on it because we have 5828, 6428, 6422, 7022, and 7622, 5 binders in a state of 2,000 square miles. So this is just using phase angle. And it gives you a relative idea of what's happened to your elastic recovery. As we saw on Greg Harder's slide with the 7622, the lower the phase angle, the more elastic it is. Same thing here. Up here in the range of 85 to 88, this is obviously a straight run, unmodified binder. It may have a smidgen of modification, you can't tell. But down here, and this is last year, 2019, the paving season. This is obviously polymer modified because of the low phase angle around minus 82, which happened about the phase angle in our reference split samples. So here we have, you can definitely see, and the suppliers, this is not limited to one supplier. They trade material back and forth. As you can see, their stock is changing. This was a few years earlier, in 2015, when we actually still had refineries in the area. Look how tight it is compared to, let me go back one, to here. Not very tight. But here, your standard grade is a fairly consistent product. And not much polymer modification was needed to make your 6428. Okay, key points for the S grade. The unmodified curve runs parallel to the modified curve on R92 if you stretch it out past, yes? At 64. Yes. That's a good point. Let me go backpedal one. Yeah, this is at 64 degrees. We run the original binder test, and that's a type on my slide which I missed. I apologize. No, sorry, that's not a typo. I'm trying to read it. That's the degrees. Yeah, we run everything, when we get a plant sample, run everything at the original DSR. It gives us a good idea. And this just shows you what's happening. So the takeaway of this is, and for any states unless they have a dedicated refinery, is you're having a moving target. You're having a moving target almost on a daily basis, depending on which supplier you get, which terminal it comes from, and for that matter, which refinery or supply source that terminal is getting their asphalt from. And they'll swap back and forth depending on what's available, what barges in, what train comes in, and what's the cheapest. And so it's fairly difficult to get a handle on a day-to-day basis. Your H grades, which is your 7022 for Delaware, do fall under R92, but as I said earlier, they don't have to be fully polymer modified, as Louisiana found out by trial and error. You can specify a negative Z to specify your product. A supplier can actually use the Z factor, either positive or negative, to monitor their product. They can monitor how much the polymer addition is. They can actually monitor how well it's incorporated into the asphalt. You saw a lot of pictures of a phase microscope with the blobs to a continuous picture. The Z will do the same thing. It will start off at some negative number and gradually creep up to a positive number. Of course, it takes a lot longer to run the RTFO than pop another microscope, but you can see the same effect. Agencies want performance. It's typical human nature to say, well, if one is good, two is twice as good, but two costs more than one. And so if you don't need a 7622 or 64E22 with a Z of 25, don't specify it. It's more expensive. We pay a premium for that product. So as an agency or anybody using the asphalt, know what works for you. And I appreciate the slide from Louisiana because they figured out what worked for them. Other uses. I look at the MSCR test as a key to see how our lab is behaving. I also use the Z factor. There's no quick fix to this. Take these slides, use them as a starting point, don't use them as an end point. See what works for you. A few years back, we bought a new DSR, different manufacturer, versus a 9 or 10-year-old DSR versus a new one. And these graphs are hard to see, but basically, it's plotting the Z factor from the COA. I just take the numbers and convert it to Z, and our test data, and you get a line running through it. Don't try to read these graphs because you'll go nuts. And so I just simplified everything, took away all the dots, and put the lines. The lines are all parallel. The slope's the same, it's about 0.93, so things are very consistent. 2015 was the old DSR. 2017 was the new DSR. You see, there's a big difference. And anything like this, you see, okay, well, the data doesn't look the same, but after a while, you start plotting it out. You can start seeing the difference. So I talked to the manufacturer. He said, oh, yeah, our applications lab, they didn't like the shape of the curve and changed this, that, and the other, thinking to make it better. Well, it changed how it behaves. Reologically, probably what they did made sense, but since we're dealing with the standard, it's not the way to go. You'd have to change AASHTO. When they changed the software back to the AASHTO way, the lines are almost on top of each other. The slope is not 1. Ideally, it should be 1. The intercept is not 0. And what you're seeing with the slope and the intercept are the inherent differences between our lab and 3 or 4 other test labs. It has to do with your RTFO. It has to do with how you prepare your sample, how you trim it. But the Z gave me a good idea of how our DSR was behaving, and it was a tool to get it changed. Okay, between lab reproducibility. They've put in the standard specs, the ASHTO standard specs, precision and bias statements for the test. This deals with a lot of data. I put everything as an absolute value so you can see it easier. This is percent recovery. Okay. Sorry. Yeah, this is percent recovery. High percent recovery is for polymer modified because your machine can actually detect it easier. It's very good, and it's probably somewhere around 20 or so percent between two labs. This would probably be the TDS percent. When you get to the standard grades or and to the non-modified, it's all over the place. I actually cut off the graph that goes higher because your DSR is having trouble getting accurate numbers. When you move to JNR, the story's actually the opposite. At high JNRs, which would be your S grades, your H grades, your V grades, your 64s and 70s for Delaware, it's actually fairly good, fairly tight. It occurs in this region. It's, what did I write down? It's probably about 10 or 15%. And so you have very good interlab reproducibility. But when you get to the modified, with your JNR of under 0.5, once again, DSR is having trouble finding the numbers, and there's a great variability between labs. And you can see, and it's probably between labs, it's probably about 40%. So you can't have one precision bias statement that covers everything. You have to differentiate between polymer modified and unmodified. Everybody see that? I'll go back one. See the difference? Polymer modified is tight for the percent recovery, lousy for the unmodified. It's tight for the unmodified for the JNR, but very poor for the modified. Okay, historic data. Everybody talks about data mining. You don't throw anything away. The world's a moving target, and Greg's thing is your old 76 the same as your 64E. And so these are two graphs. This set of data comes from really the pre-MSCR test, 2009, 2011. These are 76s, and this is a phase angle original binder. As Tom said, it's really better to use the RTFO. We have infinite data with our field samples with original DSR at the phase angle at 76. Okay. Right there, this would be the R92 line, and the slope's different. You get up to last year. Slope's slightly different because the refineries have changed their product, and so it changes. I only had 1 point just barely going to the line, but you can use this to go through your historic data to basically get an approximate Z factor. It's not precise, it's probably within 4 or 5%, but it gives you a relative idea of what you've been using over time, so then you can look at what you have today. Don't take this as an absolute, but look at it as just a tool to give you a guideline of where you're basically standing. Are you facing north or east? I really don't care whether it's north, northeast. Just give you a guideline. Am I running out of time? Okay. Conclusions. We'll do the conclusions real quick. Z is derived from the MSCR test. Additionally, Z can characterize partially modified grades as I went through. It can be a tool to gauge difference between laboratory, and you can use, as with the phase angle, to sort of look at your old data. Oops. I'd like to thank Greg Harder of the Asphalt Institute for being a champion and calling it the Z factor, Tom Bennett for supplying data and a lot of communication, and most importantly, I'd like to thank our two technicians, Lestine Spady and Quentin Civils. Their test results are so identical to each other, it's blind to the tester, so I can use years and years of data with good confidence. There they are. I have appreciated the service for years. Last of all, I went through a lot of stuff in a short time. Remember, if you're going to use it and specify your materials, do your homework. And that's it. Any questions?